Thank you, Professor Greffet. Can you hear me? Yeah, thank you for the nice talk. So we have time for questions. So anyone willing to ask a question can just turn on his microphone, can ask it, or either in the chat, if you don't have a microphone, you can nicely write your question down and I can ask it for you. So do not hesitate. So many people looks like to be very shy in the beginning, especially to ask questions. So may I ask you, so Bogdan, if you can share again the screen in the beginning. So first you were talking basically about an emitter and then putting a layer on top of it. And something that I could not perfectly understand in the beginning of the talk is how the physics of the emitter. So yes, go more. Sorry, in the other direction, Bogdan. So at some point you have a sacrificial layer in between. And you said that if you remove that layer between the source and let's say the metasurface, then it's not only that you will change the transmission, that you will change the property of the because of that, but you will also influence the source itself.
So
I think that it was not that slide. Go a bit further, Bogdan.
In the second part of the talk, you mean, or in the first part of the talk?
In the first part of the talk.
Okay.
Yes, sorry, just one back.
Oh, here, this one?
Yes.
Oh, okay.
Yes.
Do you refer to when I was discussing the concept introduced by Shan-Wei Fan with filters on on top of a surface? Is that correct?
Yes, exactly.
Yes. Okay. So here I was just saying that one simple, essentially the basic idea is to say that to control emission, you want to control the transmission of the interface. That's the basic concept. Everything of controlling thermal emission is just you have your bulk material, which is hot. There is an interface, and then you add some metasurface on the interface, and that's a trick to control the transmission. And at the end of the day, you can view your metasurface as something that produces a transmission factor as a function of K and omega. And that's it. Now, pushing this concept, you can say, okay, I can take a filter and I just grow a filter by having a multi-layer coating, just grown on the metasurface, and what happens? And it works perfectly well. So in as much as your layers are transparent, so they just do not absorb and emit. So you need to use really transparent materials. With index contrast, you engineer the transmission factor that you want. And the substrate is absorbing, so the substrate is therefore emitting because it's absorbing. And then you have just this multi-layer, which acts as a filter. And then you can tailor as you want the emission, because that's what you need to do. And then I was saying, yeah, but then why not having, what's the difference with just a black body, black paint, and then 10 centimeters away, you use a filter? What's the difference? The difference is that if you have a black body, you emit a lot of power, and an extremely tiny fraction of it goes through the interferential filter. If you grow the filter right on top of your black paint, then the only photons that leave the system are the useful ones. So the efficiency of your system is 3-4 orders of magnitude larger. Okay. And this remark is also valid for spatial coherence. You see, that's exactly what I did with this metasurface for CO2 detection. I could take black paint. I could just emit in all directions and all frequencies, and then use a filter. and then use a pinhole and the lens. And I make a source as directional and as monochromatic as I want. Problem is, I'm using all the energy of my battery, and after half an hour, all the energy is gone, and I get a few photons, basically nothing.
Yeah, I
So
totally.
that's the whole beauty of the system, is that with the battery energy, it just emits the photons which are needed in the right direction, right angle, and you save your energy.
Okay. Yeah. Thanks a lot. I overlooked actually this aspect from the energy. Do we have any question from the audience?
Hello? Hello? Can you hear me?
Yes.
Hello, Jean-Jacques. This is Alexandre Baron. Thank you very much for your talk. It was very pleasant. I learned a lot. I had a question. Actually, this is related to the previous question. You're saying, from how I understand it, basically, you're saying the efficiency is better, but this is basically because you're inhibiting the spontaneous emission at the wavelengths that are not filtered by your system, right?
Yes, exactly.
But then as a result, my question is, how is this efficiency exactly defined? Because I imagine that you are also enhancing the non-radiative emission or the non-radiative decay. And so as a result, there is a lot of energy that is actually not used to produce photons.
Okay, so thank you for the question. So this is a very good point. What you are saying in terms of relative decay is using a reasoning that is valid when you have single emitters. You excite the single emitter, so it gets the energy, and then either it emits a photon, you're happy, or you have non-relative decay, and the energy goes inside in the metal, it's quenching due to metal, and your energy is lost forever. But here, it's totally different. Here, I have a hot piece of material, the membrane I was showing, and either I emit a useful photon, or what? Or the energy stays in the membrane. The membrane is a thermostat. In as much as the membrane is insulated from the rest, the energy goes into the thermostat. It's a bath. It's a thermal bath. So yes, okay, this energy is no longer in the right phonon that was emitting the photon I wanted, but it's still there, and it cannot escape. So in as much as the energy stays in the bath, I'm happy.
I see.
So you have a phonon. I do have a surface phonon, and this surface phonon may emit a photon, I'm happy, or it may not. So it gives back the energy to the thermostat. But so what? The thermostat is there, and the energy will come back. I can try a second, a third time.
Yes, indeed.
So you are comparing with the electrical input that you have spent. So you have spent electrical power to heat the bath. But in as much as the energy stays in the bath, you haven't lost your energy. You can try again and again. The thermostat will give you another chance, another one to emit the photon.
I see.
So,
Thank you very much.
This is the dramatic difference between thermalized lights sources and two-level systems. You need to think not at the level of the emitter, but at the level of the bath when you look at the energy budget.
I see. Okay, thank you very much.
Also like to ask a question or maybe make a comment, especially that we are on this slide where we see two different designs. On the left, they are uniform spheres. On the right, we have these crosses. I guess on the right, it is because they couple a little bit much better through these arms. But I want to make an observation that by basically doubling the unit cell on the right, you get two peaks. what are those? They are just two bands and a gap, so it's a gap system. And I think it will be very easy to generate, for example, quantum Valley Hall effect in this system. One just has to put these crosses on a honeycomb lattice, and sure enough, you'll have almost for free these topological modes between domain walls.
Okay, I'm not sure. Here, the two peaks are due to resonances of the two different units. So you see we have big crosses and small crosses.
That's right.
So the resonance is really the resonance of either the small or the large crosses. So it's not a collective structure of these peaks. They are independent. It's really resonances of different emitters.
So you say the coupling is not strong enough to hybridize this.
No, they are not hybridized. Yes, there is a little coupling because it's still a metasurface, but really the position of the absorption is really mostly a localized absorption by each of these emitters. The reason why you do get close to 100% absorption for each of those is that those are dipolar emitters, and the absorption cross-section is much larger than the actual geometrical size of the devices. Okay, any dipolar absorber has a cross-section which is lambda square, roughly speaking, 3 lambda square over 2 pi. So the actual cross-section of each cross is much bigger than the cross itself. But you should look at that mostly. Let me put it in a different way. I could randomize the position of these crosses, and it would still work.
It will still work. How about if you increase the density? How close these crosses needs to be to start to see hybridization?
I don't know.
Okay, and that's not a direction one wants to go, I will guess.
Well, you can do that. You do change the properties. But I don't have a simple universal answer to this question. I think it's use a full landscape of answers.
I'm sorry, I've got a naive question. Does it make sense to have a Floquet-Bloch band diagram for this structure? Can you draw some dispersion curves or not?
Oh, yes. Well, in that case, it's a periodic array. So yes, absolutely.
But you solve which equations? I'm not too sure. Is it Maxwell? No.
Excuse me?
Which are your governing equations? What is?
Yes, absolutely. It's totally Maxwell's equation. I'm sorry if I wasn't clear.
So
everything
it says might work. You know, you can just draw dispersion diagrams, and perhaps there is stop bounds. No.
But what he's saying is that the bands will be very flat because there is no hybridization. So the bands will be flat.
I understand. I understand that, but
there will be bands. Definitely, there will be bands. You do have dispersion relations, and but what I was saying is that the resonance, these resonant peaks are mostly due to the localized structures of each substructure. So yes.
But nothing prevents the appearance of Dirac cones. You cannot say that, no? I don't know. Maybe this is silly what I'm saying.
Yes, to do an artificial graphene out of these metasurfaces, that will be a good.
Yeah.
But may I just ask, because I mean, why would you do this? Because I mean, Jean-Jacques is mainly, I mean, not only, but mainly interested in out-of-plane radiation of this structure.
Yeah.
And you want to engineer an in-plane property, right?
Yes. So to direct, for example, thermal energy through these domain walls and maybe release that one at
you could have a network is you could have a network and it would be radiating only along edges, topological edges. You know, you would have, it would be beautiful. You would see radiation from above, but just through a network. You see what I mean? It would be like, yeah.
No, I'm not sure. I don't see what you mean.
No, in fact, if you engineer, if your grating has this kind of topological properties, then the energy which leaks out of the grating would have the signature of a topological crystal. You see, the leaking would be it would be a very specific, the leaking. You would see, I don't know, it would look like aurore boreal, you know. No, I think this is nothing prevents from.
So you mean a particular specific shape as a function of frequency?
Yes, exactly. Yes. It actually would be shaped totally. Shaped thermal radiation and so on. Yeah.
Yeah, but we do see that if you move on to the right.
Next slide.
When I was showing directional sources, when was that? No, yeah, in the beginning. So excuse me, before. Here, if you look in detail, no. Yes, if you look in detail here, so this is silicon carbide. So in that case, we do have all these patches. We are exciting surface phonon polaritons. So you do see a structure with which is due to the translated surface phonon polaritons dispersion relation. So the surface phonon dispersion relation in Kx Ky is a circle. So the way we realize this directional emission at the center was to having 2p over g equal 2pi over lambda, such the way that you see the circles all crosses at the center. Okay, I don't know if on your screen you can see these circles. Is that better what you had in mind?
Yeah, but it would be way more complicated. You know, you could engineer some networks. I mean, it would. Yeah, you would enrich, you know, the control.
Okay.
So engineering, and this is exactly what you're doing. Actually, you already engineer the metasurface to have this kind of phenomena, but by adding, like Emil said, the topological twist, you might have totally new phenomena.
Okay, but yes, definitely what we see is if you plot your dispersion relation at a given frequency as a function of Kx, Ky, that's exactly what you get.
So it makes total sense to engineer dispersion relations of the metasurface to control the thermal emission.
Absolutely, that's exactly what I've been doing.
Yeah. So, and you could add, you know, this topological. I mean, it would be a new class. I don't know if anyone has looked at it.
Yes, especially that you don't. All you need is to double the unit cell. So somewhere there is you generate a gap. In the spectrum, and so that's the beauty of the Valley Hall effect, that you do it by just patterning the metasurface rather than introducing how to say and nothing else, which can be done easily. Let me say that.
Yes. Okay. Yes. Well, yeah. At the crossing points, you do have anti-crossing, and this has been observed. You do observe that in absorption, and therefore you also see it in emission. So these gaps, yes, definitely. This has been seen already. Yes.
In the last design that you showed, the gratings were unidirectional. So as I can see, the pictures were mostly one-dimensional. Can something similar can be achieved with a planner? So this one, for example, as I see it, is you control one-dimensional. So it's not a two-dimensional. Certainly, it's a one-dimensional. So is there a limitation, or this is where the research is at right now?
So with that, you can control the polarization. So you have a polarized emitter. And what we are doing now is to have much more advanced structures in order to be able to emit circularly polarized light. It's much more challenging, and you need much more complicated shapes instead of simple wires. But yeah, the idea is that by playing with this, the shape of these wires, you can structure the polarization. So this is what we're doing now.
So when you say the shape, meaning the cross-sectional area, or really maybe putting...
Oh no, the topology of the wires, of course. If it's just, you need to break the symmetry that you have here if you want to try to emit circularly polarized light.
Okay. Do we have other questions?
Can I ask another question?
Yes, yes, please.
This is Alex Baron again. I remember, Jean-Jacques, I had read a paper that you had written where you were considering non-equilibrium bodies, and you said that you could generalize Kirchhoff's law.
Yes.
And I remember that when I read this, I thought I had a question that came was, could we imagine generating pulsed thermal emission by considering something within a body that takes heat but for a very little amount of time and then releases it?
Well, so this is what we have been trying to do here with these wires by sending pulses of current so that we hit locally the wires, and therefore we have a pulse emission. So the temperature indeed is, so for instance, I was showing a pulse of current sent into this array, and we do see a light emission, which is a pulse. Yes.
Yes, indeed.
Can we see that slide? That will be interesting. It must be the next slide.
Yes, next to, yes, this one, yes. Yeah, so here we applied a pulse, a voltage pulse. So we had a pulse of current. So the temperature was by Joule heating, increasing very fast. So the pulse is in blue. So the temperature was measured by measuring the resistance of the wires. And the signal, the emitted signal is red. So yes, definitely we can have a very short signal emitted.
Okay, thank you.
And the frequency of the pulse was?
So here it's a short, it's a Gaussian pulse with the width of 10 micron. So if you look at the content of a Gaussian pulse, it has a cutoff at, say, 100 kilohertz. But when we did the test of the device by moving frequencies, we went up to 10 megahertz.
10 mega, and the emitted radiation was peaked at what frequency?
Oh, optical frequency, you mean? The optical frequency is 5 microns. So 5 micrometers.
So if we take the measured signal and we do a spectral analysis, will be peaked at that frequency?
Yes.
Uh-huh.
Yes. So this is what we did at the end. So if that was the last slide.
Last slide.
Here. So that's the spectrum. That's the optical spectrum, the infrared spectrum. And you see that on the right panel, you have the measured emissivity. So this measured emissivity is really the spectral analysis of the light emitted by the system. We divided the signal by the derivative of Planck's function. And so we see this peak at 5.1 micron. So in the design, this is really the distance between the thickness of the spacer between the mirror and the platinum wires. That is the parameter that controls that emitting frequency.
Can I ask also a question?
Yes.
The fluctuations in this right-hand figure, could they be related to inhomogeneity in the temperature distribution? That was a question I wanted to ask you. Because I missed the first quarter of your talk, maybe you already mentioned, but in general, do we have homogeneously temperature distributed devices over the whole surface pattern, the spacer and the bottom metal, for example?
Yes, I do not expect any inhomogeneity. These deviations from the simulated absorptivity are due to two factors. One of them is the fact that there are absorption peaks, and the second one is really in the way we deal with the data. When we acquire the data, we use a Fourier transform infrared spectrometer. And we are operating in a step scan mode. So in the step scan mode, you fix the position of the mirror of your Michelson interferometer. You have to average over long times because the signal is quite weak, and then you shift the mirror and so on. So it's a very long experiment, and in order to reduce the time of the experiment, which is several hours, you need to reduce the number of points. When you reduce the number of points in the Fourier transform, you start having numerical issues. So this is really a purely numerical artifact, which is due to the number of points that we are using, and this is limited due to the length. So those are artifacts, mostly.
Okay, so just a yes/no question is.
Excuse me, Jean-Jacques, it's Yannick.
Yes.
Thank you very much for the very nice and clear talk. Since you were discussing about the way you record the data, do you have a lock-in detection for this?
Yeah, of course, yes. We have a lock-in detection. And step scan mode, we have a lock-in, yes, of course.
Okay.
Without
so
lock-in,
the spectrum is superimposed on the DC component, so to say.
Say it again.
You have also an overall heating of the sample, which produces some background component.
Oh yeah, absolutely. So since we are heating with a given modulation frequency, there is an average flux.
Okay.
And the linear response to this average flux is a linear increase in temperature, which is quite significant.
Thank you very much.
Thank you. Is there any other question? I have a last question, Jean-Jacques. It's regarding the APL 2014. So it's, Bogdan, if you can go in the beginning of the talk. It's about the membrane. So you have two conducting parts, one on the bottom and actually one on the top. Yeah, click there, 19. And at some point you said you try to get rid of the conduction.
Yes.
And how do you do this? This I could not hear very well, but okay, you hit the bottom, basically in this representation.
Okay, so let me explain again. So we have a gold mirror, you see. Then on top of it we have a membrane. So the white area is vacuum.
Okay.
So the membrane is heated by Joule effect. So there are wires on the membrane which are hitting the membrane by Joule effect. And we are only hitting in the center of the disk. We're not hitting everywhere. So if you look at the upper graph, the heated part is the red part.
Okay.
So as a consequence, you have a conduction flux that goes from the heated part to the outer part of the membrane. And of course, the temperature decreases as a function of the radius. So you do get radiation from the center, which is hot. You don't get radiation from the substrate, which is cold. And in between the center, which is hot, and the contact area, the temperature is decreasing. So since it's decreasing, you still have an increase in temperature, so it helps radiating. The only way you can have energy losses is through radiation. And when you arrive at the edge in contact with the substrate, then you are cold. So if you are cold, there is no longer if the temperature has decreased, then the conduction flux is negligible, so you don't have losses. So what happens is that you have a fin in terms of thermal engineering. They call it a fin. So at the edge of the red area going from inside to outside the disk, you do have a flux in the membrane, a conductive flux. So if you were just touching the substrate, all that conduction would be lost and you would have an issue. But what happens here is that since you have a piece of membrane before getting to the edge, this energy that is conduction at the border of the heating area, this conduction gradually transforms into radiation.
Okay.
So it escapes in a useful way because that's what you want, radiation. And all the energy has cooled down when you arrive at the edge. Everything has been lost through radiation, which is what you want.
Yep.
And when you arrive at the edge, all the energy has already leaked out, and this relative leakage is exactly what you want. So that's how you suppress conduction losses.
Yes. Okay, thanks.
Just make sure that the wire is radiating. So it's converting into radiation these potential conduction losses. It's a very simple trick. Of course, it works if you are in very good vacuum, assuming that you don't have convective losses, which is not so easy.
Okay, thanks a lot for the last question. And I would like to say thank you again for the nice presentation and especially for the half-an-hour questions. So if any other people, if you have more questions, I think you can email Jean-Jacques directly, or you can comment under the video that will be available in the next few days directly on the website. So thanks a lot for the presentation, and have a good afternoon.
Thank you very much.
Thank you.
And next week is Matthias Fink.
Yes, sorry,
Matthias
I forgot.
Fink next week.
Thanks, Sebastian.
Okay, wonderful talk.
Bye-bye.
Thank you.